Today we're going to be looking at two different ways to find zeros of polynomial functions that are not factorable. We're going to look at long division and synthetic division. So for this first example, I've given you a function that has a graph. So if we look at the graph, we want to think to ourselves what appears to be the zeros. Well, going by increments of 1, this appears to be a 0 of 2. And these both appear to be zeros less than 1, but it's not quite clear. Maybe this is a half, and maybe this is 3/4, but we can't be sure, and as mathematicians we want to be sure. So what we're going to do is we're going to use a process called long division to divide this polynomial by the expression that contains the 0 and see if we can find our remaining zeros with this process. So we're going to go ahead and x minus 2, which is the expression that contains a 0 of 2, is going to be our divisor, and 6x cubed minus 19x squared plus 16x minus 4, that's going to be our dividend. And as we reviewed previous to this, long division of just numbers, this process is going to model that. Okay, so we're asking ourselves, how many times does x minus 2 divide into 6x cubed minus 19x squared plus 16x minus 4? So when we start this process, we go first term to first term. So we ask ourselves, x times what is 6x cubed? Which is essentially asking how many times x goes into 6x cubed. So we know that x times 6x squared is going to be 6x cubed. Once we get that piece of our quotient, we're now going to multiply back to all parts of the divisor. So 6x squared times x is 6x cubed. 6x squared times negative 2 is minus 12x squared. We're going to go ahead and subtract. 6x cubed minus 6x cubed is 0. Those should cancel out. Negative 19x squared minus a negative 12x squared is the same as negative 19x squared plus 12x squared, which gives us negative 7x squared. We go ahead and drop the next term and repeat the process. Notice that when I divided, I put the x squared above the x squared. That's going to tell me how many rounds I have to go for my division. So we repeat the process, first term to first term. X times what is negative 7x squared, and that would be minus 7x. So that's the next part of our quotient. I now multiply that by all parts of the divisor. Negative 7x times x is negative 7x squared. Negative 7x times negative 2 is positive 14x. We go ahead and subtract. Negative 7x squared minus a negative 7x squared is the same as negative 7x squared plus 7x squared. So those should cancel. 16x minus 14x is 2x. And we're going to go ahead and bring down that last piece of our dividend. And we repeat the process one more time. X times what is 2x, and that would be positive 2. 2 times x is 2x, and 2 times negative 2 is negative 4. We subtract, and 2x minus 2x is 0. Negative 4 minus a negative 4 is the same as negative 4 plus 4, which is 0. And thus we get a remainder of 0. So when we divided by long division, what we proved is we proved that indeed x minus 2 goes into 6x cubed minus 19x squared plus 16x minus 4 evenly with a remainder of 0, and that is our quotient. And if we look up at the graph that we started with, that proves that 2 is a 0. And this quadratic is going to contain our remaining zeros. So we did divide using long division, and now if we want to find the remaining zeros, we're going to go ahead and take our quotient and we're going to set it equal to 0, and we're going to solve that quadratic. So efficiency wise, we're going to see if we can't factor this. Obviously we can use quadratic formula, or complete the square. So let's see what we got here. Let's try 3x and 2x. And then let's go ahead. If it multiplies to a positive but adds to a negative, both of these are going to be negative. And let's try 1 and 2. 3x times 2x is 6x squared. Negative 2 times negative 1 is positive 2. And my outside gives me negative 3x. My inside gives me negative 4x, which is the negative 7x. If I go ahead and take and set each of these equal to 0, I get x to be 2/3 and x to be 1/2. So my zeros for this polynomial, the place where it crosses the x-axis, x to be 2. We knew that from the graph, and then we proved that algebraically through our long division. And now we also got x to be 2/3 and also x to be 1/2. So with a polynomial that didn't factor, we used long division to get our cubic down to a quadratic when we divided by a linear, and that quadratic contained the remaining zeros that were missing that we were unsure of when we looked at the graph. And we estimated, and I was correct with the 1/2, but 3/4 was actually 2/3, and so as mathematicians, we want to be exact. Okay? There's another method for finding the zeros of a polynomial, and that's called synthetic division. So synthetic division is set up very similarly to long division in the process, but the layout looks a bit different. So in synthetic division, you have this box, and in the box goes the potential 0, and the potential 0 is 2. And what goes in this top row is also your dividend, but just the coefficient. So if you remember from the previous page, f of x was equal to 6x cubed minus 19x squared plus 16x minus 4. And unlike with long division, I'm not going to write the x's. I'm going to go ahead and just write the numbers, the coefficients. And I have to make sure that no power is unaccounted for. So if I have a cubic, I need to account for the squared term, the linear term, and just the number, which I do. There's no skip in power. So we're going to go ahead and draw that bar. And how we start this process is we drop the 6. We drop that first term in our dividend. And now we're going to multiply. 2 times 6 is 12. Unlike long division with synthetic, you add, not subtract. Negative 19 plus 12 is negative 7. Then you multiply. 2 times negative 7 is negative 14. You're going to add, get 2. 2 times 2 is 4, and we get a 0. I go ahead and draw this little line in between the last term and the second to last term, because what this stands for is our remainder. This right here is our quotient. This right here is our divisor. And this right here is our dividend, similarly to long division. Just like with long division, we went ahead and were able to get a cubic down to a quadratic by dividing by a linear. And if you're ever unsure, once you're done with the remainder, the way you calculate this is the number, the constant, this is your x term and your x squared term, and you continue that on for all the terms that you have in the quotient. So this would be interpreted as 6x squared minus 7x plus 2. This is the quadratic that contains the remaining zeros. We know that 2 is a 0 because when we divided by x minus 2, it went in evenly with the remainder of 0. So we would set this equal to 0 and solve, and you see the parallels from what we did with long division now with synthetic division. And so it would factor the same. You would set each piece equal to 0, and you would solve and get x to be 2/3 as well as 1/2. And thus your zeros, all of your zeros, it's a third degree polynomial, it's a cubic, so you need to account for 3 zeros. And you would have x to be 2, x to be 2/3, as well as 1/2. So that's method 2. There's a third method for finding the zeros of polynomials that don't factor, and that's called direct substitution. So I'm going to go ahead and rewrite our polynomial that ends up being our dividend down here. And what we're going to do is we're going to find f of 2. So f of 2 is 6 times 2 cubed minus 19 times 2 squared plus 16 times 2 minus 4. So order of operations, I'm going to go ahead and cube this first, which is 8. 8 times 6 is 48. And then this is 4. And 19 times 4, so 20 times 4 is 80. Take away 4, because I've counted one extra 4 times, so I get 76. This is 32 minus 4. Okay? So if I add these, and again, we can do this a lot of ways, but if I take 48 and 32, I end up getting 80. So I get 80, and negative 76 and negative 4 is negative 80, and 80 minus 80 is 0. So think about what we know about functions. We went ahead and plugged 2 in, and out came 0. And that's an x-intercept, which is the same as a 0 solution or root of that polynomial. So what direct substitution told us is if that potential 0 was in fact a 0. If we got a remainder of something other than 0, it would give us a point on the graph like it did here, but that y value would have to be 0 for that point to be an actual x-intercept, because the value of y at the x-intercept is always 0. So the drawback from direct substitution is that it shows us whether or not something is a 0, but it doesn't give us an expression that has the remaining zeros that we need to know about. Okay. Let's go ahead and look at a couple more examples. So there is a restriction on when you can use synthetic division. In synthetic division, you can only divide when what you're dividing by is x minus a number or x plus a number. If we're dividing by quadratics or non-linear expressions, then we would have to use long division as opposed to synthetic. So let's go ahead and look at a little bit more practice. So A says we're going to divide our f of x, which is listed up here, by x plus 3. So we're going to go ahead and set up our problem. X plus 3 is our divisor. Now here's what's interesting about this problem. In our, what will be our dividend, it starts with an x to the 4th, and then goes x squared, x number. It skips an x cubed. Well, in our dividend, we're going to put in a placeholder for the missing power of the variable. So I went ahead and put in 0x cubed minus 10x squared minus 2x plus 4. And at this point, the process is the same as what we saw on the previous page. Ideally, we're going to go ahead and divide. We're going to get this 4th degree down to a 3rd degree with the hopes of potentially finding the remaining zeros. In this particular problem, it just says to divide. I went a step further in the first problem, even though that said just to divide, to show you what the purpose of this is. So I'm going to go ahead and start first term to first term. X times what is x to the 4th, and that would be x cubed. So I put it above, my quotient is going to align power-wise with that piece of the dividend. And then I'm going to multiply, so I get x to the 4th plus 3x cubed. And with long division, we're going to subtract. X to the 4th minus x to the 4th is 0. 0x cubed minus 3x cubed is negative 3x cubed. And I'm going to go ahead and drop my next term. I repeat the process. X times what is negative 3x cubed, and that's negative 3x squared. I go ahead and distribute this piece of the quotient to all parts of the divisor. Negative 3x squared times x is negative 3x cubed. Negative 3x squared times 3 is minus 9x squared. I subtract. A negative minus a negative is really a negative plus. Those cancel out. Negative 10 essentially plus 9x squared is going to give me negative 1x squared. I'm going to drop the minus 2x. Then I repeat the process. X squared times what is negative 1x squared, and that would be minus x. So I go ahead and multiply, and I get negative x squared minus 3x. I'm going to subtract. A negative minus a negative is a negative plus. Those cancel out. negative 2x minus a negative 3x is essentially negative 2x plus 3x. So that's x. Bring down the plus 4. And then finally, x times what is x? That would be a plus 1. When you distribute, you get x plus 3. And when you subtract, you get a remainder of 1. So at this point, when you get a remainder of 1, you know that x plus 3 does not divide evenly into this dividend, and thus negative 3 is not a 0. So we did perform long division, but we wouldn't be able to at this point use this quotient to figure out the remaining zeros because we have a remainder, and it tells us negative 3 is not a 0. Let's see how this looks with synthetic division. With synthetic division, we're going to go ahead and put our potential 0 in the box. X plus 3 would yield a potential 0 of negative 3. Now our function, I'll write it down here again, is x to the 4th minus 10x squared minus 2x plus 4. Similarly, we want a placeholder for the x cubed term that isn't here as part of our dividend. So the coefficients would go 1 for x to the 4th, 0 because there's no x cubed, negative 10, negative 2, and 4. And we should expect to get the same result in terms of the remainder. So we drop the 1, we multiply, we add, we multiply, we add, we multiply, we add, we multiply, and we add. And in fact, we do get a remainder of 1. And if you look at the parallels between the non-remainder part of the quotient, we're taking a 4th degree divided by a linear, so we should expect a cubic. And if we forget that, we're going to go after the remainder, number x, x squared, x cubed. So this would be x cubed minus 3x squared minus 1x plus 1. And then I can say remainder 1. Or I can say that the answer is x cubed minus 3x squared minus 1x plus 1 plus x plus 3 plus 1, your remainder, over your divisor. So either one of those would be a fine way to go ahead and express your answer. Okay, finally, on this last part, we're going to go ahead and figure out what f of negative 3 is. And again, let me go ahead and write down what our x to the 4th, what our polynomial that we're dividing into is. Okay, and so we get a remainder of 1. Essentially what we should expect is that we plug in negative 3 and we should get out 1 because we generated a point on our graph. And that's going to tell us that negative 3 is not a 0 because this is not an x-intercept because your y value is not 0. So let's try it just to make sure. You never have to use all 3 methods, but they all check each other out and they all end up in the same spot. So f of negative 3 is negative 3 to the 4th minus 10 times negative 3 squared minus 2 times negative 3 plus 4. And so this ends up being 81. 9 times negative 10 is negative 90 plus 6 plus 4. So this ends up being negative 9. Negative 9 plus 10 ends up being 1. So the remainder that you get when you do synthetic or long division is the same as the output that you get when you plug directly in to the function the potential 0. And again, what you've generated is you plugged in negative 3, out came 1, and from our function unit, we know that we've generated a point on a graph, just not an x-intercept.